I share screen?
Sure. Why don't I'll briefly introduce you and then hand it over to you. But go ahead. So hello everyone. Thanks for coming. It's my pleasure to introduce Dr. Lint Barrage. Dr. Barrage is Lint's dissertation advisor at Yale was William Nordhaus, who is a kind of someone that I personally have always been a giant fan of and based my own dissertation research off of. And I think her research has successfully extended his legacy by helping to bridge modern macroeconomics with the economics of climate change. Lint recently moved from Brown to the University of California, Santa Barbara. And I hadn't realized Anthony Milner had moved there also, but it seems you guys have assembled a concentration of high-profile young climate economics researchers, which is super exciting. I first became familiar with Lint's work when I saw her present her job market paper at an ERE meeting. I think it was in France, maybe in Toulouse a number of years ago. And the session she was in was one of the biggest sessions of the conference, and it included the original paper by David Hamous and his dissertation advisors, I guess, Sasamoglu and Agian. And there was a lot of buzz in the audience about how I was Lint. I was sitting next to Matti Liski at the talk, and he was rumbling about how this was the future of the field and how exciting it was. And it's exciting to see that you and David have managed to combine your talents and work together. I'm personally very excited about this paper. I think it asks a big and important question. And I think it's still very much a working paper, but it uses an elegant model to develop a number of really interesting and important policy insights. So with that, I'll hand it off to you.
Wow. Thank you, Terry. What an introduction. Exceedingly generous. Thank you for having me in the seminar. I'm really excited to be here, and I look forward to everyone's comments about this paper. So the purpose or question of this paper is to investigate the impacts of the shale gas revolution for climate change and climate policy. And as I'm sure everyone knows, over the past decade in the United States, production of natural gas from shale deposits has increased by over a factor of 14, and overall US natural gas production has increased by over 60%. So the United States has become the world's #1 producer of natural gas. And from a climate perspective, one of the most salient effects of this outward shift in natural gas supply has been an increase in the consumption of natural gas, particularly in electricity generation. So on this graph, we have the shares of coal in red and gas in green dash in US electricity generation over time. And we see that natural gas has now surpassed coal as the dominant fuel in US electricity generation. Now, from a climate perspective, this is important because natural gas emits around 40% less or fewer CO2 per BTU than does coal. So along with this change in the fuel mix of US electricity generation, we've also seen a sharp decline in the CO2 emissions intensity of US electricity generation. So that's the red line here. We've also seen a sharp decline in CO2 emissions levels in US electricity generation. So if you were to just look at the aggregate data, you might reasonably conclude that the shale gas boom has been beneficial for the climate in the United States to date. Now, the central contribution of this paper is to highlight how the long-run effects of the shale boom might be dramatically different because of its effects on incentives for innovation and the direction of technical change. So we first empirically document that the shale boom was associated with a sharp decline in green relative to fossil fuel-based electricity innovation, looking at patents data. Second, we develop a directed technical change model to think conceptually about the effects of the shale boom. And we first show that in the short run, we should indeed expect the shale boom to decrease CO2 emissions levels, provided that natural gas burns sufficiently clean compared to coal. At the same time, we also show that we should expect the shale boom to decrease green innovation certainly contemporaneously, and perhaps even permanently under suitable conditions. Now, as a result, we show that the shale boom can delay the transition to clean energy and increase CO2 emissions in the long run. Now, I should say that, of course, if hypothetically we had a policymaker who responded optimally, then the shale boom could only make us better off. But our results here pertain to an unmanaged shale boom whose welfare impacts are consequently ambiguous. And then finally, to put some quantitative meat on the problem, we developed a quantitative version of the model for the US economy to study the impacts of the boom as well as the optimal policy response. So first, our model can replicate the decline in CO2 emissions that we've seen in the short run in US electricity generation, and it predicts in the longer run increases in CO2 emissions resulting from the shale boom's effects on innovation and directed technical change. The optimal policy response to this, we find, is an increase in clean research subsidies and a weekly higher carbon price. So we're fortunate to build on many gigantic shoulders of the literature. I think in the interest of time, I'll be brief and just say, broadly, this paper is in the tradition of integrated assessment, climate macroeconomic models, and specifically the branch of this literature that has incorporated directed technical change into this class of models to study climate policy in this context, where we specifically contribute by studying the shale boom and by developing a model with the requisite features for this analysis. So for the remainder of the talk, I'll first start off talking about our empirical motivation, sort of what we saw looking at patenting data, then describe the analytic model and its results, and then discuss the quantitative model and the quantitative results. So, I had mentioned we'd seen this decline in green relative to fossil fuel-based innovation, and where that comes from is patenting data that we have been looking at. So specifically, we obtained data from the World Patent Statistical Database, or PatStat, looking at all patents. And we classify patents as relating to fossil fuel electricity generation based on a classification developed by Lanzi and co-authors. And we classify patents as relating to green electricity based on just standard patent code classifications that already exist, where we differentiate renewables from green, which is defined as renewables plus biofuels plus nuclear. And so what we see first, this is data from the United States Patent Office. So we see here depicted over time 4 different measures of green relative to fossil fuel electricity innovation. So the blue line is renewable over total patents. The green line is renewable electricity over fossil fuel electric patents. The red line is green. Again, that's renewables plus biofuels plus nuclear over total patents. And the orange line is green relative to fossil fuel electric patents. And all these series tell a similar story, which is that after a long period of increasing, so relatively more green innovation, we see a decline beginning around the time of the shale boom around 2009. Okay. Of course, this is just one country's time series, okay? So next we compare the experience in the United States to other countries that did not experience a shale boom. And one thing that's important to note about natural gas is it's not like oil in that markets are not internationally integrated. So we see divergences in natural gas prices across regions all the time. So for example, on this graph, we have natural gas price series for the US in blue and for Europe in red dash depicted over time. Well, we see that in the US, around the time of the shale boom began to decline, a sharp decline in natural gas prices, whereas in Europe, the decline did not happen until later on. And roughly consistent with this pattern, we see a similar story looking at renewable over total patents in North America, where shale boom occurred around 2009, and France and Germany, where it did not. So on this graph, we have renewable over total patents, and we see that in the US and Canada, beginning around 2009, there's a decline beginning in this patenting activity, whereas in Germany and France, we see that patents initially continue to increase and then decline also. Now, this is still just suggestive for several reasons. So first, I want to be clear, we can cut the data many different ways, and they don't all, they're not all that pretty and perfect of a story. So here, for example, is renewable over fossil fuel electric patents. This series is a bit noisier. but we do also see a decline in the US beginning earlier than elsewhere. And then next, to be a little bit more formal, we do price regressions, looking over a broader time horizon at the association of natural gas prices with green relative to fossil fuel-based electric patenting. So we specifically consider natural gas prices and their effects on patenting, with allowing for a 2-year lag for effects to occur. And we look over a time horizon from 1978 through 2015. We obtain natural gas price data from the International Energy Agency, controls for GDP per capita from the OECD, and controls for public R&D support for fossil versus green innovation from the International Energy Agency. We also include country and year fixed effects. Now, this is still just a suggestive regression in that we use equilibrium prices on the right-hand side, right? So we can't claim causality here. This is just an association, but nonetheless, we thought it was interesting to look at, since we have more controls here than just by comparing the difference in the one time period that is the shale boom. And what we find consistently across different specifications is a positive and significant correlation between our natural gas price index and renewable relative to fossil fuel electric patenting. And in a way, this is intuitive, right? If natural gas prices go up, there's more incentives to innovate in the substitute for natural gas, which is renewables. And so we see this positive association in the data. And this is robust across, the controls that we are able to make. I should also say people sometimes raise as a concern that the 2009-10, this time period and renewable energy markets, this boom bust period is somewhat pathological potentially. And I just want to highlight, even if we cut off our data in 2005, if we don't include the post-2005 period at all, we see virtually the same association, positive association between natural gas prices and renewable relative to fossil fuel electric patenting. So this positive association, of course, would then also imply that we might expect to see a negative effect if we give it a causal interpretation of lower natural gas prices on renewable relative to fossil fuel electric patenting, which is again at least consistent with what we see in data aggregates. All right, so as I said, these are not causal estimates, they're just associations, but we found them sufficiently striking and interesting to then want to work on this problem. So what we first do is we set up an analytic model to think conceptually about what we should expect the effects of the shale boom to do. So I'll first describe the setup of the model, then the short run impacts and the dynamic impacts of the shale boom that are predicted by this framework. So we have a standard discrete time economy where a final good is produced using a general production input YP and an energy composite E. So in the analytic version of the model, our production input is going to be produced only from labor. In the quantitative version, it'll be a capital labor aggregate. Our energy composite E is produced as a CS aggregate of coal, natural gas, and clean energy with elasticity of substitution epsilon. In the quantitative version of the model, generalized to allow for a different elasticity of substitution between the two fossil resources, coal and gas, and green energy sources such as renewables. So the production of each energy good, and we're really focusing on electricity here, is modeled as LTF in a resource input and in an energy input. So you can think of the energy input as a power plant. The resource input is, the coal, and producing electricity we model as LTF in you need a power plant and the coal to produce electricity. Coal and shale, coal and natural gas, both have an emissions intensity, and pollution is generated by the consumption of these resources with emissions intensity, with a given emissions intensity. So we model coal as having a higher emissions intensity than gas, and green sources as not emitting greenhouse gases. Terry, did you? Sorry, I can't hear you. You're muted.
Sorry about that. I guess the fact that you don't model the finite supply of natural gas is potentially important. Do you have any thoughts on that?
Yeah, So we consider a version of the model where productivity in extraction is constant. So then over time, the price of natural gas relative to other goods is increasing. That's not the same as having the price increase endogenously with cumulative extraction, but we do have a version of the model where scarce resource, the prices of fossil fuels increase over time, so that the model would predict a transition to clean energy even in laissez-faire. So we capture a flavor of that with one of our specifications.
Okay.
And I wasn't paying attention. If there are other raised hands that I missed, I apologize, but I'm used to interruptions, so let me just make sure there was nothing. Okay. So one of the star players in our show is going to be the technology for the power plant. Does the beep mean someone raised their hand?
No, sorry, that's someone just entering, and I need to shut that off, but I can't do it right now.
Just want to make sure. All right, so we model the power plant, this energy input, as produced as a combination of a continuum of intermediate inputs. So you can think we combine a steam turbine and a boiler and a range of intermediate goods to make a power plant. And we model each of the intermediate inputs to the power plant as produced by a monopolist using labor inputs here, and again, labor capital aggregate in the quantitative model. And the monopolist has access to a technology that's gamma times more productive than the competitive fringe, which comes from our innovation process that we'll describe later on. So the key player here is going to be the productivity in these generation technologies, which is endogenous. And notationally, it's going to be convenient for us to define as A's the average productivity levels in each type of electricity generation. So we have ACT being the average productivity in coal power generation, AST the average productivity in gas power generation, and AGT as the average productivity in green power generation. The extraction side is modeled similar to the generation side in that we model fossil fuel extraction as also requiring an extraction input, say a gas well, which is an aggregate of a range of intermediate technologies such as drill proppants, etc. The green resource, say wind, is considered free. And we're also going to define as the B's are average productivity levels in coal extraction and BS the average productivity level in gas extraction. Okay? Now, as Terry mentioned, we take coal and gas to be an infinite supply so that the resource price is simply equal to the extraction cost. Notationally, there's one more guy we have to get to, which is our C's are going to be defined as the effective productivity level of energy type I as the harmonic mean. And this it's useful because it reminds us that the effective productivity of gas generation depends both on the level of technology in gas generation and the level of technology in natural gas extraction. All right, so with this setup, we can already think about the model's predictions for what in the short run we should expect to see the effects of the shale boom. So we model the shale boom as an exogenous one-time increase in the level of productivity in the natural gas extraction sector. And we can decompose the change in CO2 emissions levels due to a change in productivity in natural gas extraction into a substitution effect and a scale effect. So the substitution effect is the change in the emissions intensity level due to the change in natural gas extraction productivity, which arises because we substitute the energy mix we use to generate electricity. So on the one hand, we would expect some substitution out of coal towards natural gas, ceteris paribus, to lower greenhouse gas emissions. We might also expect some substitution away from green towards gas, ceteris paribus, this should increase the CO2 emissions intensity. And then second, of course, because energy is now cheaper than it was before, we would expect a scale effect that demand for energy increases, which ceteris paribus would expect to increase CO2 emissions levels. And so looking at these combined effects, the first result of the paper is that the shale boom leads to a decrease in CO2 emissions levels in the short run, provided that natural gas burns sufficiently clean compared to coal.
I guess sometimes people think that there's a complementarity between natural gas and renewables. Do you think abstracting from that matters?
So, I mean, we know there's some complementarity, especially in the very short run, right? So there's a paper by Caffeine and co-authors looking at wind in Texas and gas in Texas, finding in the sort of very short run, there's a complementarity. On net, overall though, the estimates of fossil with green is that they're substitutes, right? So the elasticity of substitution estimates by Papa Giorgio et al. At sort of an annual aggregate level, they're substitutes. We have discussed the possibility of modeling a sub-nest where they're complements and then a higher nest where they're substitutes. I suspect that it might matter a little bit quantitatively, but qualitatively, I don't think. I think on overall, at a longer time horizon, they're substitutes more than they're complements. So I think qualitatively, the results should be robust, would be my conjecture about that.
Thanks.
But it's a very interesting question for sure. All right, so then with that, we can start to think about the dynamics. And by dynamics, what we're really interested here is changes in technology levels. A relatively standard specification of the innovation sector, where there's a mass one of scientists who can decide in which sector to work. So Share SF works in fossil fuel generation technology, and Share SG works in green generation technology. Each scientist has a probability of success in a given sector I that they might work in, given by eta, the research productivity, times the stepping on toes externality. If you innovate, if you go into a given sector, if you have a successful innovation, you create a technology that's gamma times more productive than the prior vintage, and you obtain a patent that lasts for one period. Okay. Now we focus on innovation, endogenous innovation in electricity generation technologies, and assume all other technologies in the economy evolve exogenously. So if we let PIT, which is a function of the wage, this gamma term, and the average productivity level of generation of type I, be the price of energy of type I, we can write down or think about the expected returns from inventors of going into different sectors. So an innovator going into the green sector obtains expected profits that depend on the probability of success in the green sector times a markup term times the revenues to be had from selling machines in the green sector. There's an analogous expression for the fossil fuel sector. And so in equilibrium, of course, innovators must be indifferent on the margin between going into green and fossil. And so we know that in equilibrium, expected profits of going into fossil versus green innovation ought to be equal. This condition then allows us to derive an expression for the predicted share of scientists working on green relative to fossil fuel innovation as a function of the parameters or the technology levels of the economy at a given point in time. Okay, so this expression now allows us to relate the productivity in natural gas extraction to predicted innovation activity in green relative to fossil innovation. And so the key points to take away from this expression are as follows. So first, the more advanced sector gets a larger market because there's larger profits to be had from further innovation. So I always like to think of this as, if I could come up with an invention that improves the iPhone or that improves the typewriter, I would rather improve the iPhone because there's a much bigger market to which I can then sell my invention. And it's a similar story here where the more advanced technology has a bigger market and hence is more attractive for further innovation. So more specifically here, better green technology leads to more green innovation, and better gas generation technology leads to more fossil innovation as well, provided that fossil fuel extraction is not too costly relative to generation costs. And what that sort of side note means intuitively is you can imagine a scenario, I like to think of a moon power plant, where if you have a power plant that burns moon rocks, extraction is very expensive. So even if you improve the moon rock boiler, it's still not going to be more attractive to build a moon rock power plant. So that's kind of, there's technically a part of the parameter space where this is not true. But for where we're going to be empirically, it's going to be the case that better gas generation technology leads to more fossil innovation. Now, we can also think with this now about the effects of the shale boom, which is an improvement in gas extraction technology. And because extraction and the power plant are complements, higher gas extraction.
Sorry, Linda.
Oh, yes.
Sorry, I think there's a question.
Sorry. Yes, sorry.
I'll let someone speak up. Sorry.
Sorry, I did not understand the sign on the exponent on phi. On C, sorry for the. So why there's a negative external in a Jones model, for instance, that exponent would be smaller than 1 but positive. So that's just a clarification question.
The C?
Yes, exactly.
We also it's smaller than 1 but positive.
Yeah, but there's a minus sign in front of it, right? So that means that in the previous slide.
It's a stepping on toes externality.
Oh, okay. So yeah, I understand. But I mean, yeah. So do you think that this is like crucial to drive the result, or or not? Because like you can think about the other. I mean, you can think about duplication activity and things like that, and stepping on toes, but you can also think about the opposite, right? Positive externalities in working in the same sector, blah blah blah, something like that.
Yeah. I mean, people sometimes have. I'm blanking on the technical term now. It's not economies of scale, but there can be the technology level to a positive exponent as well, right?
That would be say a Jones-like model. That would be like Jones 95, like that kind of stuff.
Yes. So there are alternative specifications certainly for the innovation process. I can't off the top of my head think through what the implications were of also having a positive externality term like that in our setting. I would be surprised if it changed the main story. I would imagine it would have implications more for the strength of path dependence and sort of the speed at which, I would imagine it would have implications primarily for the strength of path dependence or lack thereof.
Yeah, just since I have you, do you think that this implies too much R&D in laissez-faire, like in either of the two technologies, or not? Like having a negative externality? Because like in a Romer kind of model, you have too little R&D, right? The exponent will be equal to 1. In a Jones model, you have an exponent that is less than 1, and you have that is not going to matter for the long run growth rate, but it's going to matter for the allocation of scientists. And so here you have a clear stepping on toes externality, which implies that you should have some form of too much R&D in either sector in laissez-faire, right?
We're gonna have insufficient R&D.
Okay, even with this, okay.
Well, I mean, for several reasons, because the inventors don't get the full social value of their invention.
That's common, yes.
Right, so we have that. And relatively, if that's bigger in fossil or green, depends in our setting on which technology you want to have more of in the future, because wherever you want to innovate now, I mean, there is a shoulder of giants externality here as well that improves the technology going forward. So the social relative to the private value, how that ratio differs in the clean versus fossil sector determines which you might want to subsidize or tax.
All right, thanks.
I'm just thinking, no, I should have a better answer for conjecturing what the effects of that would be in the model. So thank you for bringing that up. That is interesting. All right.
Related to that question, yes. I'm just curious, do you solve for the optimal path of, does your optimal path at the end of your paper achieve the optimal allocation of scientists? Do you have like a sufficient instrument to do that? Like and I can't remember what the instrument is. Are you using a carbon tax, or are you?
We have a clean research subsidy, which ex ante could also be negative, and in some parts of the parameter space might be. Since we have a fixed measure of people who work as researchers, what's relevant is how they're allocated, right? We don't have an extensive margin decision of how many people work in the R&D sector. So the relative subsidy of innovating in clean versus fossil is sufficient for us to achieve the appropriate allocation of researchers in terms of in which sector they are.
Okay.
And yeah, the measure of people working innovation on the extensive margin is fixed. So yes, we do. All right, so returning to our story, I'm still thinking about it because it was an interesting point, but okay. Returning to our story, what we've said is that we've discussed some of the mechanisms through which we would expect an improvement in the gas extraction technology to invite relatively more innovation in the fossil sector. And so more formally, we show that a shale gas boom, which again we model as an increase in gas extraction technology, leads to reduced innovation in green technologies, certainly contemporaneously and permanently under suitable conditions. And suitable conditions here again means that fossil fuels are not too costly to extract relative to generation costs, such that improvements in generation technology don't really invite more innovation in generation technology. So basically, if we're not in the moon rock equilibrium, in the moon rock part of the parameter space, we would expect the shale boom to permanently decrease green innovation absent further policy intervention. And the intuition here is, again, that the effect of the shale boom innovation builds on itself over time. If you have the shale boom, we now innovate relatively more in fossil generation. We have better gas turbines. That's going to make gas more attractive. We have more gas power plants. That's going to increase the size of the market for gas turbines. So innovators have even more incentive to innovate more in gas extraction, in gas generation technologies. And so the success of the gas sector builds on itself over time. So the consequences of this change in innovation for the economy and allocations and emissions depends very much on what we assume about the future trajectory of productivity in fossil resource extraction sector. And we consider two polar cases. So the first case we consider is one where extraction productivities, the Bs, remain constant after the shale boom. So the shale boom was a one-time shifting up, and then extraction productivities remain constant thereafter. What that will do is it means that, relatively speaking, fossil fuel resources become more expensive over time. So we would, even in a laissez-faire economy, expect innovation to eventually move to the clean sector. Nonetheless, what we show is that a shale boom in this setting delays the clean energy transition and increases CO2 emissions in the long run by delaying the transition to a clean economy. The other extreme case we consider is one where fossil fuel extraction productivities continue to grow at a constant rate after the boom. So we've just shifted up their path, but they continue to grow. In this setting now, we have path dependence, and the innovation allocation is bang, bang. And what this means is that, or what the shale boom does in this setting, is it makes the fossil fuel path more likely, okay? So in particular, there's three cases we can think about. So this is a setting where, again, path dependence is strong, meaning where we predict the economy to go, absent policy intervention, depends on where we initially are with technology levels across different sectors. So first, if initially green generation technologies are relatively backwards, right, we would expect the economy to move to an all fossil fuel future, because again, the successful sector invites more innovation, which then invites more innovation, and the success builds on itself. So if we're in a world where initially green technologies are relatively backwards, we would expect the shale boom to hasten the transition to an all fossil fuel future. Second, there's a range of initial green generation technologies where we might have been at the point where, even without further policy intervention, we would have transitioned to a green economy. If green technologies are sufficiently advanced that they take off, we would have expected to go to an all-green future. It is possible for the shale boom to kick us off this path back to a path toward an all-fossil fuel future, so that we delay the transition to a clean economy permanently. So there's parts of the parameter space where the shale boom can permanently delay a transition to a clean economy, barring further policy intervention. And then finally, if green technologies are already sufficiently advanced, it's possible that even with the shale boom, we would still expect to transition to an all-green economy. However, even in this setting, we would expect the shale boom to delay the transition to a green economy, thus potentially increasing CO2 emissions in the meantime. So these are some theoretical possibilities. And of course, we're interested quantitatively with where we are in the parameter space. So I'll first describe the setup and quantification of our model, then describe the results from a laissez-faire setting. And if there's time, I'll also discuss policy and an extended version of the model that relaxes some of the assumptions we make in the benchmark version. So as I mentioned before, we now generalize the model of the production sector to the general production input to be a capital labor aggregate, and also the production of the power plants, the energy input, and the production of the extraction input are now all capital labor aggregates. As I mentioned, we now also allow for a different elasticity of substitution between coal and natural gas than with green. And this is to capture, for example, intermittencies and other reasons that green electricity is not equally substitutable for coal as is natural gas. Next, we also now model local pollution abatement policies and local pollution abatement costs, for example, sulfur dioxide. So the price of electricity, for example, from coal is now going to depend on the resource price of coal, the power plant input price for coal, and also on abatement costs that are mandated in coal generation. And the reason it's important for us to account for this is when we go to the data and we want to infer what technology levels are, we don't want to mistake high expenditures for backward technology, say in coal generation, if those high expenditures are driven by mandated expenditures on abatement technologies. So we quantify our model using microdata of US electricity generators' costs and outputs. So most of these come from FERC, the Federal Energy Regulatory Commission. We obtain and construct estimates of local pollution abatement capital expenditures with EIA data, and we also collect information on fuel resource costs that power plants pay from FERC and from the EIA. FERC does not have ideal coverage of renewable and particularly smaller renewable generators, so we supplement this information with Lazard estimates of levelized costs in green and renewable technologies. There's a number of parameters we take straight from the literature. So we take the estimate of the elasticity of substitution between fossil and green electricity from Papageorgiou et al. And as we discussed with Terry, this is an estimate of 1.85. We take the elasticity of substitution between coal and gas, also from the literature. And same for the elasticity of substitution between energy and other inputs in aggregate production, and for the labor shares in energy versus the general production sector. We quantify our gamma parameter based on industry profits data from the US Census, and we take 2006 through 2010 as a model base period. Importantly, we model the shale boom, or we quantify the shale boom as a 100% increase in gas extraction technology levels. And this is based on what we see in the data in relative coal and gas resource price changes over our initial to base model time period. All right. So with that, we solve for initial technology levels. Again, these are the star players in our show, and our energy aggregator distribution parameters to jointly match a number of moments, including GDP, electricity generation, generation costs, and employment shares that we see in extraction, electricity, and general manufacturing. Terry, may I ask you the time? My clock got shut off, just so I can.
Yeah, sorry. It's 12:42, so you have about 15 minutes or so.
Okay, perfect. Thank you. All right. So with that, even before quantifying innovation, we can again think about the model's predictions for the short run impacts of the shale boom. And so through the lens of the model, we predict that the increase in gas extraction productivity should decrease the CO2 emissions intensity of electricity generation by 13.5%. Now, you know, our model is a 5-year time period. There's not a perfectly analog number in the empirical literature, because most empirical papers look at very short run effects on the emissions intensity. But Cullen and Mansour estimated 10% decline in the CO2 emissions intensity of fuels electricity generation in the short run. And just looking at the raw data, we see an emissions intensity decline of 11.35%. So this is arguably within that same ballpark. Model also predicts an increase in energy consumption, but on net, a decline in CO2 emissions resulting from the shale boom in the short run. The model sensitivity is sort of as you would expect conceptually, but I think in the interest of time, I'll just move on. So next we want to quantify dynamics in the innovation sector, where we need to quantify first the probability of success that a scientist going into a sector may have. And we quantify those ADARs to ensure that the long run growth rate of the economy on a balanced growth path can be 2% per year, regardless of whether the economy ends up in a green or fossil long run equilibrium. We set this stepping on toes externality parameter to match so that the model matches our empirical estimates of the elasticity of green innovation with respect to the natural gas price of about 0.35. So we also need a carbon cycle and climate change impacts. So we take the carbon cycle and damages from Golosov et al. Now, we only model or endogenize greenhouse gas emissions from the United States electricity sector. So obviously we need to account for rest of the world and US non-electricity emissions. Our benchmark model takes these as exogenous from the Rice model. We've played around with some emission spillovers both to the US electricity sector and to other countries. If I have time, I can talk about those results, but they're in a way not as interesting as you might have thought. We adopt a period of social time preference of 1.5% per year, standard value, and an elasticity of intertemporal substitution of 1/2. I should also say in the quantification, we let capital grow exogenously since it's not really central to our analysis. So with that, we're first going to think about the effects of the shale boom without policy intervention in a laissez-faire setting. And we're again going to be looking at results in those two polar cases for what we assume will happen with extraction productivity in the future. The first being constant extraction technology. So again, this is the setting where fossil fuels get more expensive in the future. We predict even in laissez-faire, the economy moves towards a future, but the shale boom delays this transition. So more specifically, in panel A here, we have the share of scientists working in fossil fuels. The green line is without the boom. So because we predict that the cost of fossil fuels will increase in the future, we predict a transition to a clean economy. Eventually, fewer and fewer scientists will innovate in fossil fuel resources. What the boom does, which is depicted here in blue, is that it sharply increases the share of scientists working in fossil fuels, and it delays this transition away from fossil fuels over time. The corresponding economic and emissions impacts are as follows. So we see initially this decline of about 5% in CO2 emissions levels, but over time, as fossil technologies become relatively more advanced, we see this effect reversing, and the effect, the percent change, I apologize, I should have said the left axis here is percent change over time in each of these variables. The percent change due to the boom of emissions becomes positive. So eventually we have higher emissions because of the boom, while initially we had lower emissions because of the boom. Looking at the effect of the boom on output, we also see that initially the shale boom increases output, but eventually over time, because of the increase in CO2 emissions, we see higher climate damages, we see a negative effect on output in the long run. Terry, yes, sorry, you had your hand up.
Oh, no problem. I was just thinking that the way you model technology is important in getting the sort of super long run effects of the shale boom, in the sense that I could imagine, it seems to me, I don't know if this is plausible or not, but if instead the shale boom was modeled as an increase in the stock of accessible natural gases, if there was a finite supply of natural gas and you increase the stock that's accessible, then it's not clear you would have you would have the same long run persistent incentive to continue to invest in the decline of that technology, because there's only a certain amount of shale gas in the earth. And if we develop technologies that allow us to access it, it's not clear that it just continues, that we can continue to access more and more and more by investing more in inventing more horizontal drilling or something like that. So it seems like there could be a world where the way in which you model the technology is hugely important for getting these kind of results. I don't know if that makes sense.
My gut reaction is I believe that our model is actually consistent with your story, but let me make sure that I understand it correctly. So in our framework, we're not predicting that shale production will continue to increase over time in this particular slide, right? This is the relative change due to the boom. So this version of the model, where natural gas becomes more and more expensive over time, predicts that natural gas production and consumption will decrease over time continuously. It's just that that decline of fossil fuels is delayed by the initial increase of the shale boom, and the fact that shale generation technology becomes better than it would have been without the boom. But here in this setting, it's not the case that we continuously expand the supply implicitly of shale. I mean, we're not capturing resource scarcity, but I would conjecture that what you're saying would turn out to be similar as the story here, because we're not continuously increasing the extraction productivity. We're not continuously increasing the effective supply of shale. It was just the one-time increase that we're modeling here.
Okay. I see. So it's only so that scientists are going into production of fossil fuel, not extraction.
Yes, they're only they're improving the generation, the gas turbines. They're just finding more uses or better uses for the gas. They're not continuously increasing gas extraction.
Okay, thanks.
But it's interesting that you mentioned that, because we've gotten the opposite comment too. So one could also argue that we're wrong in terms of having this shale boom be this one-time event. Why couldn't we continue? You know, in the Arctic, maybe we can drill for gas better, and there's many countries that haven't had a shale boom yet. There's so many shale deposits around the world, right? So maybe we should expect there to be continuous shale booming. That's sort of an opposite comment that we've also received.
I can imagine if I mean, this is outside your model, but if you had a north-south model, that the optimal policy in the north would recognize the fact that this boom in shale technology is going to lead to much higher future emissions when China and India have their own shale booms or whatever. But that's a more complicated.
It's such an interesting question, though, I think, because for China, I mean, we've long talked about maybe calibrating the model also for other countries, because it so depends, right? If you have initially coal being very important, like it is in China, then the benefit of a shale boom replacing some of that coal with gas would be correspondingly bigger as well. So I think it's a very interesting question. Yeah. Yes, so thank you for raising those points. Next, we can also think about this sort of other world where we assume extraction productivity continues to increase exogenously after the boom. The boom just gave it an extra boost initially. And so here, with what we saw for in terms of the parameters of the productivity of green generation, is that we're currently still sufficiently backwards that absent policy intervention, we would not expect the economy to move to a green future. We would expect a transition to an all fossil fuel future. So an increasing share of scientists working in fossil fuels. And what the boom does here, depicted in blue, is that it hastens this transition to an all fossil fuel future. In terms of the effects on our key variables of interest, we again predict that the shale boom initially decreased CO2 emissions, but would then, after a while, increase them and continue to increase them over time relative to a no boom scenario. Output, again, initially increases. This is small, but is positive. And then eventually, as the shale boom has caused more CO2 emissions, causes more climate damages, we see a decline in net output relative to what it would have been absent the shale boom. Now to, get a little bit of a sanity check on our model, we can compare what the model predicts for some key variables with what we've seen in the data since. It's one of the benefits of working on a paper for many years. You have data to compare your predictions to. So in the data, we see the ratio of green to fossil patenting drop from a base period number of 1.47 to 0.99 in 2011 to 15. Our model predicts, this is not a targeted moment, a decline of 1.31 to 0.98. So this is arguably a similar order of magnitude. This is true both for the constant extraction productivity future scenario and growing extraction productivity scenario. Now, so far we've discussed a laissez-faire results. And now, of course, we want to also think about, well, what would the optimal policy response to the shale boom be? So we're going to consider a social planner who maximizes US welfare and takes in the benchmark emissions from the rest of the world and from US non-electricity sector as given. So there's going to be free riding and US policy is not going to be sufficiently ambitious. We have two externalities in this framework, and we're going to give the planner two instruments. So one is a carbon tax to correct the environmental externality, and the other is a green research subsidy or a research subsidy to take into account that, again, the private value of innovation is too short-sighted. And so in the interest of time, I'm going to focus on presenting optimal policy results for the constant extraction technology scenario, where, again, fossil fuels become more expensive over time. So first, to think, set ideas, this slide shows the optimal policy levels in the absence of the boom. So without the boom, what would optimal policy look like? So first, optimal policy should hasten the clean energy transition. So we now have in panel A, the share of scientists working in fossil fuels, where the blue line is laissez-faire and the green line is the optimum. So again, we're now in a setting where even in laissez-faire would predict the world to eventually move off of fossil fuels, but in the optimum, we would like that transition to occur faster. So in order to accomplish this, the planner would implement a clean research subsidy that's increasing over time, and also a carbon tax that's increasing over time. With the boom in place, the effects on this optimal policy package are as follows. So first, the boom increases the optimal green research subsidy by several percentage points and increasingly so over time. And second, the boom also weakly increases the optimal price on carbon emissions. So the boom calls for higher clean research subsidies first and foremost, and also slightly higher carbon pricing. Terry, I apologize for the interruption. May I get a time check again?
Yeah, sorry. Maybe 4 or 5 minutes, and then I think people might have to leave to teach, but you can keep going if necessary. So a number of people will probably stay around, and some people will have to go. So.
All right, I can give the main idea of the extended version very quickly. So basically, in our benchmark version, we had assumed that all fossil innovation advances both coal and gas generation, right? We only had researchers working in the fossil sector or in the green sector. And we have an extended version of the model that allows for distinct innovation in gas versus coal. Our benchmark model had also abstracted from sort of baseline or business as usual policies that already exist, both as innovation subsidies that already exist for coal, gas, and green, and generation subsidies and taxes that exist in the real world for coal, gas, and green. So we're now going to add these to the model. And this question of to what extent is innovation in gas or coal generation technology shared between coal and gas is an interesting one, because some technologies, if you think of boilers, if you invent a better boiler, that's going to help both coal and gas generation. If you invent a better way of coal pulverization, that's really only going to help coal generation. So we now allow for some fraction chi of a given coal innovation being specific to coal, and a fraction, sorry, I said that the wrong way around, fraction chi of a coal innovation spills over to gas, and a fraction 1 minus chi is specific to coal. So we're now going to have 3 sectors in which scientists can work, and we're differentiating coal versus gas versus green innovation. We also, again, now allow for R&D subsidies for generation taxes, and we quantify those as best as possible. And I think since I'm running short on time, main punchline is the effects that we project from this extended model are very similar to the benchmark model. So here in this table, we have the static short-run effects while technology is constant, and the predicted change in the emissions intensity due to the boom changes from 13.5% to 12.5%. If we vary the parameters of initial taxes and subsidies, it's 13.5, so really quite similar. And then the dynamic effects on innovation would predict, if anything, that the switch between the boom having decreased versus increased CO2 emissions will happen sooner. So by 2066, in the benchmark model, we predict a zero effect on CO2 emissions. In the extended model, we already see an increase by then. But really, the differences are very small across the benchmark and extended model. So to conclude, once again, this paper is motivated by the fact that if you look at patenting data, you see the striking decline in green relative to fossil fuel-based electricity innovation beginning around the time of the shale boom in the United States. And so we develop a directed technical change model to study this issue both theoretically and quantitatively. And we find in both perspectives that the boom decreased CO2 emissions in the short run, but increased it in the long run through its effects on innovation and the direction of technical change. The optimal policy response to this is stronger climate policy, particularly higher green research subsidies. Now, as we already touched upon in some of our conversations, there's a lot of open questions. For example, as Terry brought up, the cross-country differences in baseline shale boom impacts, right? What would the welfare effects of the boom be different in Germany versus China, countries that have very different initial technology and resource endowment levels? What are technology spillovers and their implications? There's a lot of interesting things to work on, but I think I'm out of time, and so I just want to thank everybody for your time today. Thanks.
Thank you very much. Are there any questions? Looks like oh no. So one question I had when you were presenting the optimal policy, you said that you modeled it so there's free rider incentives. So does that mean that the U.S. only internalizes 10% of global climate damages, give or take? So it's not internalizing global climate damages, because it would be kind of interesting to see the alternative simulation where you internalize global climate damages to see what's the, because in effect, the US is ignoring the harm it's doing to the rest of the world by pushing technology that's going to have climate damages on the rest of the world. And you don't see that in your simulation.
No, that's a really, really interesting point, actually. We could give the US some altruistic additional utility losses from damages in the rest of the world, right?
Or or even just knowing what the difference is. Like if it internalized the full world's damages, how different would optimal policy be?
Ooh, I love this. Thank you. Yes, we will definitely look at that.
Cool. I think Travis has a question too.
Yeah, I guess it relates to kind of how much technology or the innovation is baked into the system, right? This is a story of a boom, but we've seen busts as well, right? So what happens if there's that one-time sort of tech boom, right? But followed by the, what a bust, I guess, look like, right? Is it just the inverse of all those, of that story?
So I think through the lens of the model, it's a little bit unclear. We don't model the world as forgetting or getting worse in technologies, right? So I'm not sure what a bust in a technology would look like, sort of, how to think of that in terms of the model. I mean, in the real world, right, we see declines in coal extraction productivity. We've seen declines during time periods of increased regulation of coal extraction. But if it's a regulatory wedge that causes effective productivity to decline, that's not quite the same as a bust. So I'm trying to think of what that would be. A bust. It would have to be something that declines technology levels, right?
Yeah, I was trying to think through it too. I mean, obviously it's generally a price shock. That would be what we think of busts, right? Sort of the industry falling out. But I don't know what that would mean. I was also trying to figure out what that would mean for that one-time innovation, right? You jump up with the technology. Yeah.
Oh, I see.
Yeah, maybe it's just outside of the model. That's fine too. Yeah.
No, I think I understand the question better now. So if we had some shock to the market, for example, where the size of the market suddenly declines for something, that would then change innovation incentives.
Well, anything that we've seen like within the last 2 years, right? I mean, the shale boom is it still going on?
I mean, technologies are still available, right? Prices of natural gas are still lower. So in that sense, yes, but it's been difficult for a lot of the natural gas companies because fossil fuel prices are so low, right? Demand is so low. Right. So what would be the effects of a demand shock like that? I'll have to think about that carefully because I would imagine it depends on where in the model we model a demand shock. I would imagine it depends on where it's coming from in the model. That's an interesting question.
I was also thinking along those lines because the demand for electricity is changing, especially with the changes in the transportation sector going to electric vehicles and stuff. And so you could see a demand shock in the other direction, you know, huge increase in the demand for electricity by 2066 or whatever your model goes out to, which could, I don't know what that would do, but just I was thinking about that.
So, you know, conditional on the model that we've written down, that shouldn't change the innovation side of the story because everyone's innovating in electricity. It just matters which type of electricity. So if demand for all electricity shifts up and down, that shouldn't matter for the innovation side. But what I think what you're getting at, which is really important, is that matters for spillovers, right? We've assumed no spillovers from the electricity sector to emissions from the transportation sector. Right? We're taking transportation emissions as given, but to the extent that we electrify more vehicles, then emissions from the electricity sector have much bigger implications for emissions from the transportation sector, for example.
Yeah. I have another question. So I've been trying to think about this for my energy econ course that I teach. I've taught for the last 5 years that natural gas is cleaner than coal. But I've been trying to dig into the life cycle emissions literature to understand exactly how much cleaner it is. And it's certainly cleaner, but not as cleaner as we thought. So I'm curious what emissions you're using for natural gas. And if you aren't using life cycle emissions, if you were to use life cycle emissions, how would that change the optimal policies? It would probably make them lower, right? The carbon tax would be lower if. Maybe I'll let you talk about it.
Yeah, no, so my understanding of the literature is, I mean, coal also has life cycle emissions from coal mine methane, right? So the methane emissions from the extraction process affects both. And my read of the literature is that even when you take life cycle into account, natural gas still per, whatever megawatt hour is about 50% cleaner. So my understanding of some of the, the recent reviews I've read is that ratio is actually similar once you also take on the coal side life cycle emissions into account. But I also understand there's there's disagreement about those numbers, right? And it doesn't take much on the EF, the emissions factor in the gas extraction process for that number to change. I mean, what it would do if shale gas was dirtier, it would just make it look less and less favorable in our model, right? The short run emissions decline would be smaller and smaller, and the switch to the shale boom having increased emissions would just happen faster.
Yeah, but so the optimal tax, though, right? That would be right now, because of the shale boom, the optimal tax is higher than it otherwise would be. But if the shale gas emissions were higher than we thought they were, then it would mean that optimal tax is lower relative to what it would be without the shale boom. So it seems like having natural gas being clean in the model is actually beneficial in terms of saying that we need a stronger policy. I'm thinking of like an advocacy, more of an advocacy thing than.
It's an interesting question, but I'm not sure. I mean, the carbon tax is higher in part because we increase emissions and we increase damages, right? And that would be true also in the story you're saying of, so either way, right, with gas being relatively cleaner or not as clean, either way, the point of the story is that in the long run, we're going to increase emissions and increase climate damages.
Yeah.
So I would conjecture that the higher carbon tax would actually be true in both scenarios.
I think you're right. It's just like this little change in how much higher it is.
Yeah.
Yeah. Okay.
Yeah. Yeah.
This kind of a, oh no, Anders, please.
I have a question about, so I'm kind of new to these directed technical change models. I don't understand them very well. So how do we think about this in a global context? I mean, so I heard you note that inventors are only getting some portion of the benefit they create with coming up with new technologies. Do you also think about, like, I mean, how much of the benefit of new technologies accrues to the country in which the patent was made, or how do we think about this on a global sort of level?
That's I've been really interested in that question. Because I think it's so important and relevant, but I'm not sure that we know all that well, right? So in our model right now, yeah, like you said, we don't consider spillover effects in other countries. We've experimented with a version where we allow the change in US emissions to be mirrored in the rest of the world with some elasticity. So we have some spillover elasticity for other sectors, both in the US and the rest of the world. And we have a spillover elasticity to other countries. That actually that increases the optimal US carbon tax a lot, because by decreasing US emissions, you can now also have a benefit in other countries, right? But it doesn't really change the damages or sort of the levels of some of the other things. And the reason is the initial decline in emissions from the shale boom then also happens in other countries. The later increase also happens in other countries. So if the rest of the world mirrors both the emission benefits and the emission increase, on net, it's not that different in terms of sort of the emissions levels and the damages levels. But the optimal carbon tax is a lot higher once you have spillovers to other countries, because again, you get more emission reduction bang for your buck.
Okay, no, that makes sense. And then, so the decline though that you see in patents and renewable energy in other countries where they didn't have a shale boom, like, is that, what exactly is driving that? I mean, I saw that the US decline was, first, but there were big declines everywhere.
It's interesting. I mean, we can only conjecture, I think. I mean, we did see natural gas price declines happening in Europe later on. Also, to the extent that in the US, there's on the margin a reduction in the market for green technologies that should, since the US is a big enough market, that might also affect innovation incentives in other countries. We might expect that to the extent that markets or inventors were expecting more shale booms in other countries to occur as well, that might also have just shifted expectations. That might be one of the mechanisms. But how to decompose the change into these and other unknown factors, I don't know. I think it's an interesting question.
Aren't a lot of the patents, say in Germany, though, just a reissuing of a technology that was already invented in the US and they're just patenting it to cover it in Germany? Or maybe that's filtered out.
We look at both only restricting it to domestic inventors, so only your domestic filing or all of the filings, and it's a same story basically.
Oh, interesting. Okay.
Yeah.
Greg, do you have anything to add to that? There's a patent expert on the call, but I don't know if he's even tuned in.
No, that seems reasonable to me. Thanks.
The other question, well, I don't know, maybe I'm just beating a dead horse because it's the thing that keeps running around in my head, is just like I think it's potentially related to the resource bust question as well, but I could imagine, I mean, an alternative way to model it, which is not going to be analytically tractable in any way, and it's probably non-convex and has all kinds of problems, but I could imagine a world where you have two types of deposits, like accessible by conventional technology and accessible with horizontal drilling, say. So you get the easy deposit and the hard deposit, but they're both finite, they're both fixed. You have a certain amount of fossil fuel you can access. So what the shale gas boom does is give you access to the second deposit. And in either case, as you extract more, your marginal costs of extraction are rising as you extract more. So you can run into a world where you get access to this bigger deposit, you run up the marginal extraction costs because you've gotten rid of the super easy to access stuff, marginal costs are rising, and eventually it gets outcompeted by other things and you have a bust or something. But it seems like that world would have very different implications for the long run, like in the kind of stepping on the shoulder of giants technology assumption. You're getting a permanent new technology that's always more productive at producing natural gas-based electricity, but that's not necessarily what's going to happen if it's just getting access to a finite stock of natural gas in a reserve that has rising marginal extraction costs or something like that.
You know, that's a really interesting point, that the way of modeling the technology level as sort of constantly increasing wouldn't be appropriate if we have different deposits that are exhausted at one point, right? If the technology is sort of deposit specific. Again, we're not modeling, the first version I showed, there's no improvements in production of extraction after the shale boom, right? So that kind of is at least not going against your story. We don't assume there's any improvements in extraction technology after the shale boom. Mm-hmm. So that is consistent with then the costs increasing. But yeah, if we were to endogenize extraction sector innovation, then that's an interesting point, that in reality, the technologies might be deposit specific. Yeah.
It also, this feels like another piece when you think of the international problem, is that we're part of why we're shooting ourselves in the foot, or the shale gas boom isn't as great as we think, is there's now there's more fossil fuels accessible that the world has a temptation to burn. And so we've now given China access to its own, in principle, that technology will eventually give China and India and Africa access to the same. They're dirtier, well, not dirtier actually, but they're harder to access deposits. Is that your baby?
It's my dog. I'm sorry. She apparently has to use the bathroom. Excuse me. So sorry.
Sorry, I'm sorry for confusing your dog and your baby. No, I'm kidding.
She's the other baby.
We have one of those too. My dog loves to jump on my lap when I'm on Zoom calls.
Oh, I saw a cat tail also on someone's lap earlier. That was enjoyable. Someone was asking a question.
I'm not sure who that was.
Yeah,
sorry, Andrew, do you have a question?
You know, this is not maybe tied to the model, so if people have a better one, but what's the opportunity for essentially these patents or this innovation to make its way into the power sector, right? So I'm imagining Fort Collins probably somewhere has a power plant. There's a technology innovation. Do they get plugged in mostly on new plants, or is there room for a 30-year-old power plant to get new technology?
My understanding is that there's definitely room for a 30-year-old power plant to get retrofitted with some new technology. I mean, we've seen a lot of coal to gas switching, right? So a lot of coal power plants were converted to gas. And I would imagine that replacing a boiler or a pulverizer or something happens.
Happens all the time. I go and visit Rawhide, our power plant, every year with my class. They update every single year.
Thank you. That's the answer I will give from now on.
Yeah.
That's awesome. You guys visit the power plant?
Yeah, every year except this last one.
Can we get a tour? Invite us.
Yeah, you can join.
You have to sign up for Jesse's class.
Yeah, right. Well, it's all online now. You can watch it.
Great.
Thanks, Lint.
Thank you all so much. This was fun.
Good to see you.
Yeah, I wish we could have you out in person, hopefully another year.
The day will come, right? All
Awesome.
right. Thanks so much, everybody.
Thanks so much.
Bye.
Yeah, great paper.
Thank you.
Thanks, guys. Good to see you, Travis and Jesse. You been mountain biking?
I went once. You should stop recording.